Welcome.
Well, hello, everybody. Well, today, let's know if it works. Yeah, today, well, I will divide my presentation in first a small update of the status of ZisK, and then I'm going to go a little bit deeper in how to build the easy proof, especially for the proving systems, how to use this to build the easy proof and see all the advantages that ZisK have to build that proof and what are the challenges that are there. If we talk about ZisK, as many of you know, ZisK is an open source ZK-VM. It's based in RISC-V, 64 bits. It's fully open source. It's fully quantum resistant. It's 128-bit security. And today we, I don't know if this works. Yeah, today we are announcing what's ZisK 1.0 alpha. So 1.0, what it means is, I mean, we just freeze the code. We say it's alpha, so everything is there, everything is in place, everything can be used, UX is used. We don't want to call it like a final, I mean, we don't want to remove the word alpha because the security, I mean, I think we believe, I mean, we strongly believe in security, and we are not still 100% confident. I mean, we just changing some lines of code a few weeks ago. So we are not 100% confident that there is no soundness errors and so. And in today's days, AI is taking an important place for auditing by formally verifying all these smart contracts, and this is very much the current work that we are doing right now. But especially for projects that they are building their own proofs, system is there, is available, you can start using. And yeah, we believe that's quite deliverable, except for this auditing. That's going to be the main work for the next month. Okay. We're also introducing what's kind of a toy, but it's a ZisK F1. This is a full Ethereum client. It's a stateless client. And it's optimized for ZisK. Actually, this is with this client proofs can be, so we get between 10 and 50% earnings in proof cost. And it's full client designed from scratch using AI. I mean, it's interesting to mention here that right now writing a full Ethereum client in 2 weeks is crazy. It's a crazy thing, but something that you can do it today. Okay. Okay, let's go to the easy proof. Okay, so well, Martin already explained what's easy about synchronous composability. You know this challenge here. So what happened? So when we're talking about the synchronous composability, what's really happening here? Well, what's happening is that we have one call at some point. So we have one transaction that at some point is calling a smart contract that's another chain, and then returns and continue execution. So we see this kind of context switching. I mean, you are running in one chain, you context switch to another chain, and then you go back to the other chain. So easy. So in easy, mainly what we do is we collect all these context switching between chains, and we can put them in a lock. I mean, it's also all the things that sequentially are happening. So I start a transaction. This transaction is doing a call to another chain. This other chain do a return, and then we end the transaction. Okay, and we can set up this in a lock. You can understand that this is going to be in the blobs. Okay, and all these calls, I mean, or returns, all this context switching, they are going to be in a blob, okay? So that they actually, and if we summarize easy, is we have current states of the rollups. We have these logs of things that are happening, can be transactions or calls between calls, and we just want to prove that these state transitions that are happening in these different chains are consistent with the blobs that are there. Blobs are well format, are consistent, and all these generate the places. And of course, when these calls affect the L1, because everything that happens in L1 is actually executed following the same rules. Okay? But from the proving perspective, this is very much so what we need to prove. I mean, this consistency between the states that we are changing and the locks that are happening here. Okay? This is a more complex idea. So here is, instead of having one rollup and one call, here we have 3 rollups. Each one calling one another, and with nested calls, and you can add even an extra thing here is that can be reversed. I mean, these calls can revert, so maybe there are some states that they just need to revert to some specific state. So things are a little bit more complex, but at the end, it's just a lock of things, of context switching that are happening. Okay? Another important concept, I mean, before going deep to the proof, is the idea of the state transition function. Here is we call it action-driven state transition function. With it's a very specific. It's a little more deep. I mean, in a normal chain, you have a state, you process a transaction, and you get a new state. Okay. In this case, we don't have only transactions, because I mean, when we have a call, I mean, this is not really a transaction. It's just each of the pieces. So it's something. It's a piece of code that's executing in a given moment. So I'm doing a call, and maybe the result is so the end of this action is that this call is not a return. It's maybe calling a nested call in another chain. Okay? So we have this idea of, so we have an action that can be a call, it can be a return, it can be a same transaction, and you execute something, you change the state, so something is happening here, and then you get a new state, but you get another action that happens continuous. Maybe this action can be an end transaction if it's the end, but it can be maybe another call or a return to the previous call. Okay? We have also, I'm going to pass here, we have also some revert info that this state transition function can give if there are some reverts that happen there. But this is important. So, and this is very much what a chain needs to define. I mean, these rules is what a new chain can be defined. These rules can be Ethereum if it's an EVM chain, but it can be maybe a WASM chain, or it can be any sort of chain. The nice thing of Easy is that each chain can define their own state transition function, and it's full control of this. Okay? So if we see the call, I mean, if we see the proof and the things that we need to prove, it's mainly we need to prove three things. Well, the first is we have these blobs. Okay, so we have these locks of context switching that are happening, calls, returns that goes from one place to the other. Okay, this is a blob, so we need to parse these blobs. So we do all this is encoded in blobs. So we need to parse these blobs. Okay, check that the consistency, everything is matched, so that there is no lost calls, and so that everything is correct in there. Okay, this is what each blob proof. So we can have a blob, and then I get a blob proof, and then the consistency of these blobs. Okay. The other thing that I need to verify in chain is these action-driven state transition functions. So I want to prove that each of the individual contexts. So it is these green squares there. So these parts are essentially correct according to the rules that the chains define. All these chains, they define it via a verification key of a specific circuit. Okay? So this is the ADSTF proof and adapter. This is what's doing these parts. Okay? And the other part that needs to be done in the proof is collecting all the information that comes from L1. I mean, I want to build a proof that, if you start with this state, or I need to collect, for example, the verification keys of the different chains, or I need to collect all the interactions with L1. So everything that happens to L1, and it's something that's going to be in the smart contract, in the call of the smart contract, I need to verify that this is correct according to the lock that's happening there. Okay? So we have like three pieces. We have like these three big proving parts, okay? And then all this needs to be aggregated, and at the end generating a proof. Okay? In order to do that, in ZisK we are using it's what we call, it's a cryptographic accumulator. Okay? The idea of a cryptographic accumulator is kind of a hash function, but the idea is not, it's for sets. Okay? So the idea is that if you have two elements and you hash them, if you hash normally, it depends on the order. Okay? The idea is that in an accumulator, when you have two elements and you hash them, it doesn't matter if you switch or reverse them. Okay? So this is the idea of the cryptographic accumulator. Okay? And the cool thing of this structure is that in ZisK, it allows you to have like many proofs, okay? And each proof can add things to the accumulator. It can add elements, which are hashes of something, and can subtract things from the element. Okay? And the full idea of building this proof is that we can divide the work of this proof in these different accumulator, and when we aggregate, at the end we are adding or subtracting this accumulator. So aggregating is just adding the accumulator. And at the end, the accumulator needs to be 0. So everything that's added needs to be subtracted. Or if you want everything that's proven, so when we want to, actually when we assume something, we add something to the accumulator, and when we prove that assumption, then we subtract that in the accumulation. So at the end, everything that's assumed is proved. Okay? So if we see these different pieces, for example, when we are processing a blob, actually, what we are proving? Well, we are proving that the blob commitment, so the blob commitment that will come, somebody is, I'm proof that this blob commitment is correct. Okay, so in this case, I'm subtracting from the proof there. What I'm assuming? I'm assuming that the starting rollup state at the blobs, the starting or the rollup states that happens at the rollup are given ones. Well, I'm assuming this. Okay, and I'm proving that at the end of the rollups, this is going to be the state. But in order to do that, for example, I need to assume that the state transition functions of each of the states are correct. Okay? So if you see, for example, in the next, in the adapter, in the state transition functions, actually what here I'm proving it, so I'm subtracting them. So whatever I'm assuming when I'm parsing the blob, I'm assuming that this state transition function is correct. When I'm parsing when I'm verifying the state transition function of a given slice of a rollup, I'm proving, so I'm subtracting. So at the end, everything that's assumed, it's added, it's subtracted. So at the end, it needs to be 0. Okay. What else is here? Well, I'm assuming here, because this is they have different rollups. So here I'm assuming that a given rollup ID has a given proving key, so that the state transition function is so if I'm using this rollup, I'm assuming that this rollup is ID, and somebody needs to prove that this rollup ID has this exact verification key. Okay, and also here I'm assuming a lot of L1 transactions. So for everything that is an L1 transaction, I need to assume that actually these transactions are in the hash or are in the L1 transaction. Okay, and this is where the third part. Is the hash composing. I mean, this is just taking a lot of parameters and composing a hash. Okay, the hash of an L1. So here is all the information that's coming from L1. Okay, so in this case, for example, I'm taking all the blob commitments. So here, this proof actually is building a hash. So I'm taking all the blob commitments as I'm there. I'm putting them in. I'm building a hash. So with this, I guarantee that the blobs that I parsed in the blob provers are actually the ones that comes from the L1 that's telling me that are happen in the L1. This is how I link what's happening in L1, what happens in the proof. Okay? In the other side, I have all the starting blob rollup and the ending blob rollup. So the rollups is keeping all the rollups, and this is very much, so the starting blob rollups, this is, again, this comes from so this comes from the L1. So everything that's coming from L1, here I'm proving that in L1 is there is some state transition functions. Okay, and then in the blobs, I'm assuming. So this is what I'm assuming is what I'm starting. Here you see that when I have like different blobs that they connect each other. So the starting of a blob is added, and so the ending of one blob is added, so it's subtracted, and the starting of the next blob is added. So one cancel out each one. So at the end, you have in the accumulator only the starting point and the ending point. Okay, and this is what when I'm meeting the hash, this is what actually I'm putting in the hash, and this is what the information that I'm putting to the L1. Okay. Of course, here I'm hashing all the L1 interactions. All these L1 interactions needs to be in the call data when I'm submitting a blob. And this is going to be some structures that will be in the smart contract that are the ones that will be executed, in easy, so that when there is some rollup 2 that's calling a rollup 1, this code is executed in L1 and the other way around. So when something is happening in L1, that's calling to L2, well, all this interaction is recorded here so that everything is proved in the L2. So all these L1 interactions are also proven here, assume when I'm parsing the blob there. Okay? And finally, and this is important, is the verification key for each rollup. This is this is important and tricky, okay? Because verification key is variable, okay? So this is so I'm here. What I'm saying is I'm proving. So because this comes from the hash, so here I give the warranty that the proving key has this verification key, okay? And in the blobs, so I'm assuming so these are this rollup and the verification key. Important to mention here that this is these two ideas. We have the proof and the adapter, okay? And this is a trick, interesting trick that we are doing here, because we are proving something that's variable. So we are proving something, we are proving in advance, I mean a rollup, so you need to have a prover that's proving something in advance according to some verification key, because I mean a rollup that it will be added next year, it will have its own state transition function. So it will have a circuit with its own verification key, but we need to guarantee that this everything matches. Okay? So the idea here is that we do one recursion level. So the circuit will define its own state transition function, its own circuit. It will have its own verification key. This is what will be configured in the smart contract. Okay? And it's going to be one trusted smart contract, this adapter, that recursively will verify this other circuit according to the verification key, and will add to the accumulator of the full proof that will prove that this state transition function for this rollup is correct. Okay? And having this idea of this adapter that connects, so it's a double proof, I mean, that verifies, is what allows us to prove things that are not defined yet, because they are depending on the verification key. Of course, the circuit needs to follow some certain rules, but because it's just the verification key is very short. But that's the full idea of the easy. Okay. Once we have this, of course, we have the aggregation circuit. The aggregation circuit is just very much is proving. So here, so the aggregation circuit it just takes two proofs of any kind, and it adds the accumulator, and it proves both sides, okay? And it generates a new proof, okay? And you can aggregate until there is just one single proof, and then there is a final, and there is a final circuit that actually verifies this aggregation circuit plus the L1 hash proving, because in L1 you have only one hash, so you have a single one. And finally, we have the Plonk. So once we have this proof, we can convert it to a Plonk, so that's easily verifiable on chain. Okay? And well, and here is a challenge. I mean, we need to build all these proofs. We need to build all these proofs really fast. I mean, ideally in a time block. Okay? So this structure, what allows is this model. And it's important to say that, for example, so when we are building a proof, at that point, we can start so when we're building a batch of transactions, we can start building the proof very much at the beginning, as we are adding, because we are creating a blob. I can start generating the proof for that blob. And creating a transaction, I can start generating all the state transition proofs for those transactions. And the cool thing of this is that aggregation, first, is super fast. So one aggregation circuit, it takes like about 80 milliseconds. And the second advantage is that this aggregation does not require any order, because the idea of this accumulator don't matter. The hash is exactly the same. So you can aggregate as you generate. So you generate two blobs, you can already aggregate them. Okay, you aggregate. So the idea is that the last 3 seconds, this is when we are doing the final part, or we are trying to reduce this. But the idea is that when we reach this point, that we stop building it, the remaining work for generating the proof needs to be minimal. Okay? So this needs to be in a pipelined way, and this is one of the important properties of ZisK that we are building. Currently, we are in 3 seconds. We believe that we can go even lower on there, but this is the real challenges that we are working for easy. Okay. As I mentioned before, currently in ZisK we are very much, so we just launched 1.0, so it's very much about auditing, going deep, using AI for formally verifying and there are some, well, just focusing, stabilizing this circuit, okay? And of course, in this building all this easy proving system, so that works as soon as possible. And here is a list of course, in this we have a list of other topics that are interesting, but are a second priority at this point, okay? So, but it's like, well, one is quite important, is moving, so I don't know if people know, but so there are some concerns about Poseidon functions. Actually, Poseidon 2 is somehow deprecated. People is going back to Poseidon 1. And it's possible that we may have some version for Blake, because I mean, cryptographers don't like these arithmetic functions. And for us it's important. And the other things are things about optimization. This BA, improvements. I mean, there is a lot of other things that are interesting. Okay, so I want to finish here and absolutely open for questions.
Thank you very much. We have time for 2 questions for Jordi. Does anybody have a question they want to share? Yes, up here at the back. We can get a microphone up there. Give us a couple of minutes. You're a long way away.
Hi. I was just wondering, when you think of like synchronous composability and what it can do for rollups to kind of have like atomic kind of cross-chain interactions, do you think that kind of like paradigm could benefit mainnet itself? Like if you were trying to pursue some kind of like native sharding, could you kind of use this technology to actually use like create one big L1 essentially, instead of relying on like separate L2s, if you know what I kind of mean?
They are not, I mean, yeah, these are 2 models, but this is like thinking that you can scale, I mean, you can do all the computations in the world in a single processor, okay? So definitely there is a lot of motivations for having L2s. Of course, one is to split the work, especially, for example, when an L2 has a lot of transactions that they touch only, the L2 only transactions, you can process much more of them. So first is the capacity, okay? But the other thing, and this is probably the one that I like more, is that this allows you to extend Ethereum. I mean, this idea is not only, so having many rollups is not about, it's not only about doing Ethereum bigger. It's extending the functionality of Ethereum. This allows you to build your own chain that maybe is specialized for voting. Or maybe your chain is a private chain with your own rules. Martin before was talking about opinionated chains. And you can have a chain that, I mean, definitively you can decide to change the state root if there is a hack from an attacker. This is not acceptable from the Ethereum perspective, but may be perfectly acceptable, actually required in a specific rollup. So this is another motivation for having rollups. So the idea of having many chains, it goes beyond the scalability, which it does. It's more about extending, about building, expanding Ethereum, expanding the functionality of Ethereum, and making Ethereum more specialized for different applications, keeping the essence of Ethereum, which is the composability, so that one chain that maybe it's private, that belongs to some exchange company that has its own rules, it should be able to call maybe Arbitrum or call some smart contract, some Uniswap calls. A chain, of course, will have the same rules. I mean, a chain will see that it's receiving a call and it's giving back a return. Okay? And when you are connecting to this chain, you will get a call and receive a return. And if you want like an oracle, okay? But you don't depend on that. Another important thing that I mentioned here is, and this is one of the designs that we are not mentioning very much, but this is important and easy. So in order to follow a chain, you don't need to follow all the other chains, even if you connect to those chains. Following a chain is just following L1, following those blobs, extracting the information because in these things you get all the inputs and outputs that you get from your chain. So you can extract all this information, so you can rebuild your state of your chain, ignoring what's happening in the other chains. You are just getting what affects to your chain. So this allows to scalable, so having different chains, so not everybody have to synchronize everything. You are synchronizing your chain, the other is synchronizing your chain. Of course, maybe the composer, if they need to connect to chains, the composer probably will have to synchronize both chains. But it's just the composer, not an RPC client that's just providing some information. So it has a lot of advantages. So it's, I mean, and to be clear, I mean, I want Ethereum to scale as much as we can, and we need Ethereum to scale, and it's important that L1 scale as much as important. Among other things, because, for example, one of the limitations, if we are talking about one of the limitations of Easy is, for example, the data availability. We're talking about the blocks. We're putting a lot of information to the blobs. So we need high data availability in Ethereum. But one thing is the blobs, and the other thing is the Ethereum, I mean, each chain, okay? Haven't talked about validiums, okay? Validiums, again, it's perfectly possible for validiums to connect easy. The only thing is that the state, the difference is that in order to build the full state of a validium, you need some extra information that comes from other sources. This is perfectly valid because you are setting up you are setting the state, okay? The only thing is that in order to do calls to these chains, or the other way around, the composer needs to have access to this data. Okay, but because there is this independence, other chains that connect to this chain, they don't really need to have access to the full Validium chain. They need to have access to the interactions, that this is what's happening in the blobs.
Okay, thank you very much, Jordi. I don't think we have time for another question, but if anybody does have more questions from Jordi, I'm sure you'll be able to find them in the conference. Thank you very much. Next up, we have another easy-themed talk. I'm very proud to welcome Philipp Schomels to the stage. Philipp is the head of infrastructure at Gnosis. In most Dappcons, he has the job of coming up and talking about glamorous topics like hard forks. Today, he has something even more exciting. He's here to talk about the technical implementation path for Gnosis Chain with the Easy framework.